Hi, my name is Francoeur,
I'm Andrew Valenti.
and the project that we did in Section 1 was the one-lunger engine. The one-lunger engine is a single-piston, four-stroke engine. This particular one is a model. Here you can see our assembly fully put together. As you can see, there is one piston pumping up and down, and another yellow piece pumping up and down, which is a valve which allows fuel to enter and exit the engine. As we go below it, you can further see the piston pumping up and down at a faster rate than the valve, allowing for 2 strokes for every 1 stroke of the valve, as this is a 4-stroke engine. As we continue to watch the engine turn, you can see all the parts that hold the engine together, including 2 cylindrical holding brackets, and a bearing bracket to make sure that the flywheel stays straight the entire time.
For the part design of the one-lunger engine, most of the base features of the parts were cylindrical in shape. So the shaft tool was mainly utilized to rotate a profile, and then features were added to the part, most commonly holes for screws to fit through or shaft bearings. The most difficult piece to create in this project was the cylinder holding bracket, mainly because it was missing fillet dimensions, as well as its widthwise dimension was incorrect with allowing it to fit inside the assembly with the other pieces, so the dimensions had to be slightly modified for that one width.
As Andrew just mentioned, the cylinder holding bracket had several incorrect dimensions, or dimensions that were incorrectly defined, or conflicting dimensions. One of the dimensions that I would like to, bring to your attention is this 17 right here. This view here was provided to us in the dimension drawings that were provided for us to create the parts. It took us a while to figure this out, but this is actually an unfolded sheet metal view. It's something that's commonly used in sheet metal design, but not commonly used a lot of other places. So this 17 here actually has the length of the flat surface, like an auxiliary view would, of the actual slanted plane, along with the top view of the flat plane here. You can kind of see down here what I'm talking about. So the 17 would go from about there to there. Well, the rest of it would be this 8.8 here. Now, one of the dimensions that was actually incorrect about this part was the 30 millimeter dimension here. Originally, this dimension was 30 millimeters, when in reality, it should have been 30.4. We figured this out when we tried to put the piece together in assembly design and realized that this screw here didn't line up with the actual cylinder that the piston went into. So if our screw holes aren't lining up, then obviously the part must be wrong. Then we had to go back and spend several attempts trying to figure out how to finally make this piece correctly. Eventually, once we realized that this dimension was incorrect, it became a little bit easier and our holes lined up, and we were able to figure out what was happening with the part. I would also like to draw your attention to this 1.5 millimeter thickness here. So the entire part is 1.5 millimeters thick, with the exception of the fillets. If you assume that the entire part is 1.5 millimeters thick, then this fillet winds up being a weird number, like 0.109 millimeters or something like that, when it actually says at the bottom of our sheet of dimension drawings that all of our fillets and rounds are 0.1 millimeters in radius. In reality, we had to make this a 1.5 millimeter fillet to fulfill the actual specifications of the drawing. So that was unmarked. And in addition to that, this piece in the middle here was undefined within its own plane. So there was no real good way to figure out what this dimension between this point and this point was until we realized that this unfolded view had to be converted into an actual useful auxiliary view. As I just mentioned, that unfolded sheet metal view isn't really helpful in machining this piece or in modeling this piece at all. The better way to go about dimensioning it, as I discovered, was to make an auxiliary view. So these are my dimension drawings that you see in these 2 little bubbles. The first one is the front view down here, and then I also made an auxiliary view AA over here, which allowed me to properly define the top of this little cutout here to the bottom of the piece, as well as the bottom of the cutout to the bottom of the piece, and the thickness of the walls. That saved me from doing a lot of trigonometry and a lot of extra unnecessary math in that unfolded view. Yet, still, I can get the same information that I could have gotten out of an unfolded view by getting dimensions like this 65.5 and this 30.4, which has been corrected since we had issues with it being 30 millimeters previously.
The main assembly for the one-lunger steam engine was broken up into 5 individual parts in the assembly, as well as 3 sub-assemblies. The first of the 3 sub-assemblies is the frame of the engine, which consists of static parts that are coincidentally constrained to keep them concentric with the screws in the holes, and contact constraints to have the surfaces touching that will be screwed together. The second assembly is the shaft assembly, which uses the concentric constraint to have everything centered around the shaft, as well as an offset constraint to position everything accordingly, as well as angle constraints to have everything properly offset angle-wise from each other. The third assembly is the crank plate that is actually inside of the shaft assembly, and it is the counterweight in the main part of the crank weight fastened together with 3 screws.
As I had stated earlier, one of the goals of dimensioning that we had was to make all the parts easier to model and easier to machine. One of the big issues with making parts easy to machine is not calling out the center of holes from edges. A lot of times when we were looking at the dimensions that we had to make the parts, we noticed that holes were being dimensioned to the edge instead of to the center. Obviously, you can't put a drill bit on the edge of a hole and expect a hole that has a center a little off from that. That's not how drills work. So we dimensioned everything to the center lines of holes and did our best to do symmetrical dimensioning for pieces that were symmetrical along one or both axes. A lot of the dimensions that we did were hole dimensions and hole callouts, as this particular project had so many holes and so many threaded holes that needed to be called out in dimensioning. Dimensioning in this project was time-consuming, but not overly difficult. Like I said, a lot of it was just changing the dimensions that were already existing into dimensions that were more readable and baseline dimension instead of chain dimensioned. Like I said, the dimensioning style was changed a lot. A lot of the pieces had these weird views, some weird cutout views that didn't really seem necessary, and then other pieces that didn't have offset sections or cutout views at all that we deemed it necessary to have them with. But overall, the dimensioning on this project was not too difficult.
The isometric views were added to visualize the parts all assembled together. The bill of materials was created based off of assumptions of what the materials probably were for each specific part, because the sheet we were given with all the dimensions did not have any materials listed on them for us to work with. So what we went with was having most parts being made of iron, while all the standard parts that were in the engine were made of steel. The exploded views are added to easily identify which material is what on the bill of materials with balloon leaders. Generally, the balloon leaders are added to each of the parts individually, but we had 10 screws that were identical, so rather than have 10 balloons or 10 arrows coming from various balloons, we decided to just label one of them to avoid over-cluttering the drawing.
As far as team dynamics went on this project, there were really no issues. The general theme was borrowed from Nike, kind of just do it. For the most part, we kind of just partitioned up work based on who had more free time. Towards the beginning of the semester, Andrew had a lot more free time, so he did most of the original parts, whereas later in the semester I had more time, so I did the drawings. Overall, it was just kind of, the theme was whoever had free time can work on it, and whoever didn't, not to worry about it until we had to.
We utilized OneDrive to pass files between us, when we finished our respective parts, we would upload them to OneDrive so that the other member would know what we had done and what still needs to be done for the remainder of the project. Because I had more time at the beginning of the semester, I started off doing a majority of the parts, while Leo did a few in his spare time, and then afterwards I created the assemblies.
Then, like we said earlier, I made the dimension drawings and put them on sheets, and I created the exploded views along with the bills of materials and isometric views on the drawing sheets for our project. I was the primary creator of this presentation.
And I was the primary writer of the written report.